In this video, we are learning why things are acidic. Why? Why do we have the pKa's we have? Now, you could go through and look at the pKa table and start to develop an intuition about it, but we're going to talk about this in detail. These concepts you've been honing already in this course. What affects acidity? There's 5 main things. The first is, what element is this proton on? Okay, what element is attached to that proton? This deals with electronegativity and the size of that atom. The next most important thing is the charge of the atom. Then we're going to talk about resonance, hybridization, and the induction effect. All 5 of these help us determine which molecules are more acidic than others, and it is exactly why we see the pKa's that we do. If I were to just take HA as just a generic acid, and I dissociate them, I'll have an H plus an A minus. And we know that this A minus is considered its conjugate base. And here we have our acid, okay? These two are related. And the thing is, if this A minus is really happy being A minus and holding a negative charge, that's going to make it more likely for HA to split apart, right? So the more stable this A minus is, the more likely this HA will act as an acid and give up its proton. These 5 factors affect this. Let's first talk about the most important one, which is the element effect. An atom directly attached to the hydrogen has the greatest impact on acidity. If we just look at, let's say, these 4 elements, carbon, nitrogen, oxygen, fluorine. A lot of organic molecules have these. Let's just consider a hydrogen on each of these atoms. So let's just take methane. We'll take ammonia. Water. And we'll take HF, or an acid here. The generic pKa's here of these protons are as follows. pK of around 50 for methane, the pKa of around 35 for ammonia, pK of around 15 for water, and for HF it's around 5. Now, we know that fluorine is a lot more electronegative than carbon. Fluorine is the most electronegative element. So, when we start to think about what happens if we lose this proton, it's going to become really clear why HF is so much more acidic than, say, methane. So, if I lose a proton from methane, and I get this carbanion, right? We're going to do the same for this nitrogen here. We're going to end up getting 2 lone pairs on our nitrogen. So I'm just showing what happens when these act as acids. This oxygen here would have 3 lone pairs. This would be hydroxide. And then HF would be this F minus. When I look at these 4 conjugate bases, remember these are acids. And then when you remove the proton, these are now called conjugate bases. We're really looking at, can this atom hold the negative charge? Is it cool with losing that proton? And one of the best ways to look at this is this electron affinity or electronegativity. If this molecule loses a proton and it now has more electrons, is it okay? Is it stable? Is it happy with the negative charge? Fluorine is most likely to lose that acidic proton than the other 3 options here because fluorine is really electronegative. It wants electrons, so it's totally happy with having a negative charge. However, if we move to something that's much less electronegative, like carbon, it's like, this negative charge is really heavy for me. I don't really want to carry it myself, right? So As you move to the right in the periodic table, you're going to increase electronegativity. And the stability of this anion or the conjugate base increases. So again, we're trying to stabilize this conjugate base. If it's more stable, it's more likely to form. And in the case of HF, it's more likely to lose that proton than, say, for methane, because fluorine is totally happy with holding that negative charge. Now, another thing occurs with this periodic trend when you look going down the periodic table. So if we just look at our halogens, as you go down in the periodic table, the size of the atom increases, right? We've got more neutrons and protons and lots of electrons happening. If I were to just compare the size of these, maybe fluorine would be about this big, chlorine would be about this big, bromine would be like, look around you, the size of the room you're in, and iodine would be all of Camp Randall, all right? So the size of the element also affects this, okay? And if we look at what happens when we go from HF, when we dissociate into F- and H+, okay? And we do this for all 4 of these examples. It's hydrogen bromide. And we're just looking at the likelihood of them dissociating. The size is increasing as we go down the periodic table. Remember that our atoms have a nucleus that is positively charged. It's got protons and neutrons. As the size of our atom gets larger, okay, these extra electrons aren't really causing any issues. For fluorine, these extra electrons are right beside the nucleus. As you get to iodine, the extra electrons are nice and dispersed on this atom. Now, obviously, an atom isn't that big. I'm just trying to give you a visual to understand that when you have an atom that's that large, compared to fluorine, those extra electrons are nice and dispersed around the molecule. That means that I- is actually more stable. So not only does the size increase, but the stability of this anion increases. It's not only electronegativity, it's also size. As you go down in the periodic table, these elements are larger and can hold a negative charge more efficiently because the charge is spread out on that atom.
You've got to be kidding me. I thought HF would be a stronger acid because fluorine is more electronegative. Well, if the size of the atoms increase that much down the periodic table, then the bond length must also change. Oh, there it is. So because iodine is so huge, that makes the HI bond longer and weaker than the HF bond. Iodine has electrons dispersed out into the 5p shell. Okay, so if the size of the atoms increase significantly going down the group of the periodic table, the bond length increases significantly going down the periodic table, that means that's a weaker bond. So HI has a weaker bond, and that's why that hydrogen can come off more easily. That's why it's so much more acidic. Oh. All right, I'm hungry.
Because of this, we can fill in and understand the pKa's for these different acids. The pKa of HF is 5. The pKa of HCl is -5. The pKa of HBr is around -7, and the pKa of HI is around -9. So we've talked about protons on different elements. Now we're going to talk about protons on the same element. Let's take, for example, ammonium. So I've got 4 hydrogens here on this nitrogen, and I'm going to compare it to ammonia, which just has 3 protons. Now ammonia is neutral. Ammonium has a positive charge on our nitrogen. Now the pKa of ammonium, this proton here in pink, is around 10. The pK of ammonia is much higher. It's around 35. Now, why is this? Well, if we think about the charge on this nitrogen, this formal positive charge is really also telling us that the electron density wants to go towards the nitrogen. The dipole moments on this ammonium molecule are going towards the nitrogen. We know that hydrogen is less electronegative than nitrogen, so these dipole moments are in line with our formal charge. Now, if this is the case, that means that that proton, it's more like an H+. Whereas for nitrogen, it's neutral. There's nothing on this atom that's making those protons even more acidic. So this charge effect is simply saying that if you have an atom with a positive charge, it's likely that the hydrogen bound to it is more acidic than its neutral sibling, okay? So let's do one more example. Or let's take hydronium. So let's take a protonated water molecule versus just water. I'm going to highlight the proton we're looking at in pink, and we're going to look at the pKa's. So the pKa of hydronium is around 0, and the pKa of water is around 15. So this positive charge on our oxygen is, again, creating this dipole moment. That means this proton here is easier to access. The electrons between the oxygen-hydrogen bond are closer to the oxygen, so it's easier for it to be removed. That's why it has a lower pKa and is more acidic. Now, this effect is less important than the element effect, which is the most important one. So take, for example, HCl, right? We have our hydrogen here. HCl, we know, has a pKa of around -5. The pKa here is actually around -7. Look here, HCl is still more acidic than an oxygen with a positive charge. So the element effect is the biggest effect that we have. So HCl is still more acidic. Than a protonated water or a protonated amine. Indicating how important this element effect is. What element is bound to that hydrogen has a huge effect. The next effect is resonance, and this tends to be a smaller effect than the element effect, but it's helpful when we compare 3 different molecules that all have an acidic proton on the same element. So all of these protons are on an oxygen. I'm going to highlight the most acidic proton of these molecules in pink. Okay, so these protons are all on oxygen. There are no charges on any of the oxygens. Remember when we talked about HA dissociating into H plus A minus. The stability of that A minus helps us determine if HA is cool with losing that proton. If A minus is more stable, HA is more likely to break up into H and A minus. We want to favor the more stable side. So the best way to do this is to draw what you get when you lose a proton. So in this case, for this alcohol, we'll get an alkoxide For this phenol example, we'll have this phenoxide plus H plus. And then for this carboxylic acid, we'll end up getting a carboxylate. Let me label the protons here in red or pink. I haven't decided what color this is. It kind of looks pink. Maybe it's because I'm drawing it over blue. All right, so when we do this, this is essentially our A minus, all of these anions. Now we could simply just look at the three molecules and look at the pKa's and decide which one is more acidic. But this video is about why, right? Let's go ahead and do that though, just so we can confirm what we're doing. So for an alcohol, we know the relative pKa is around 15. Great. What about for a phenol? It's around 10. And what about for carboxylic acid? It's around 5. Okay, so based on these pKa's, our carboxylic acid should be the most acidic molecule here. Is that the case? Well, the easiest way to do this is to draw the conjugate bases. And you're going to ask yourself, is this negative charge happy? Is it stable? And if we compare these three, you'll notice here that for the alcohol here, we have an oxygen with a negative charge. This negative charge is being held fully by the oxygen. What about the phenoxide? In this example, well, we could draw resonance. And this resonance is showing us that this negative charge isn't fully on this oxygen. Because it is bound to an aromatic ring, this negative charge is spread out. Remember that resonance, shown by this arrow in pink, these resonance structures are just depicting where the electron density is at on our molecule. We can draw them, for example, what I have drawn in blue for this phenoxide doesn't tell us the whole picture of where those electrons are placed. That's why we use resonance structures. It's all of the resonance structures combined that tell us where the electrons are at on our molecule. There is no resonance for this example, for this alkoxide. However, this phenoxide is resonance stabilized. Resonance stabilization means that the formation of this conjugate base is favored. Let's see if that is the case when we compare the pKa's. The pKa of an alcohol is around 15, and the pKa of a phenol is around 10. This is more acidic, and it's due to the additional resonance stability. When this phenol loses this proton, it is more stable because of resonance. So that's why it's more acidic than just a regular alcohol. Let's look at another example. We have one more that is even more acidic than phenol. This is acetic acid. Acetic acid has a carbonyl directly bound to this oxygen. We could draw a resonance structure. My resonance arrow here, showing that that negative charge is actually spread out over two different oxygens. Now, we know oxygen is very electronegative, and so both of these resonance structures are really good resonance structures. They both can carry that negative charge. It's because of these reasons that this molecule is even more acidic. And again, it is resonance stabilized. Now, you might be asking yourself, well, hold on, I can draw more resonance structures for this phenol derivative, this phenoxide that I have here in the middle. I can draw more resonance structures. Now, notice though, where are the anions placed? They are placed on carbons around this ring. They are placed on carbons around the ring. In the case of acetic acid, we have two really great resonance structures that have negative charges on very electronegative atoms. This is why the pKa of acetic acid is lower than the pKa of phenol. Even though phenol has more resonance structures, the resonance structures for acetic acid has two oxygens with negative charges, okay? So it's not necessarily how many resonance structures you can draw, it's what's holding that negative charge, okay? So just know that the resonance effect does have a big effect on the acidity. More resonance stabilization of your anion means more acidic.
Vanillin is a phenolic aldehyde. Its pKa is actually 7.4, so it's a little more acidic than a normal phenol because of that aldehyde, which is an electron withdrawing group. Still, it is less acidic than a carboxylic acid, which has two major resonance structures that carry the negative charge. Okay, here's what I really wanted to tell you. Vanillin is a common flavor chemical, and it is the primary component of the extract of the vanilla bean. So you've probably eaten a phenol before, and I love ice cream too.
Hybridization also has a huge effect on acidity. Let's label the pKa's of these three hydrocarbons. The pKa of a regular sp3 hybridized CH bond is around 50 or greater. What about an sp2? So here we've got an sp2. I'm just going to label the hydrogen we're looking at here in red. Okay, this one is around 44, and for an alkyne here, this pK is around 25. Let's go ahead and draw our conjugate bases. So if we were to lose a proton, it'd be really hard to do it on this compound here, on ethane. But if we lost that proton, we would have this lone pair and an anion. We can do the same for ethylene here. All right, we're gonna lose that proton in red. I have a lone pair and a negative charge, and we're gonna do the same thing for acetylene. You'll notice that this is based on hybridization of our atom. And now molecular orbital theory will haunt us. I mean, help us. Okay, so you have an sp3 hybridized carbon, right? Now, remember when we talked about hybridization, we have an S, a P, and a P orbital for each of these carbon atoms, right? If we mix all four, we're going to get an equal mixture of these orbitals in four different orbitals, which are sp3, 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 and sp3. Very cool. Well, what does that really mean? sp3 means that we have 3 parts p and 1 part s. So this orbital that's holding this lone pair has 25% S and 75% P. Let's go through the next two. We have an sp2 hybridized carbon for ethylene. sp2. When we mix for an sp2 hybridized orbital, remember that we are mixing an S, a P, and a P. We have an empty P orbital. So we have an sp2, sp2, and a P. Remember that the P orbital is being used for the double bond, right? It's a pi bond. and it uses its p orbital to make that bond. So this negative charge is hanging out in an sp2 hybridized orbital. Okay, well, an sp2 hybridized orbital means it has 1 part s and 2 parts p. So it's going to be around 33% s character and around 66% p character. Okay, well, what about this sp? So we've got an sp hybridized. We know for sp what we're doing is we're only mixing an s and a p orbital. I'm just mixing 2 of them. We have 2 p orbitals that are being used for these pi bonds. Okay, pi bond here, pi bond here. So if this lone pair is here, it's in an sp orbital. Well, what does that mean? Well, the orbitals being used on this carbon are an sp, sp, a p, and a p. Okay, this means we have 50%, 1 part s, and 1 part p. Well, what the heck does that mean? Well, let's review real quick. An s orbital is this sphere, and here's our nucleus. A p orbital is this dumbbell shape, and our nucleus is right here in the middle. When we are looking at acidity, remember we're looking at the stability of the conjugate bases. Our conjugate bases here are carbanions. So carbanions have negative charges. So carbanions are this. We're looking to see if any of these carbons are cool with having a negative charge. Well, here's the thing. So an element with more s character has this orbital that is a sphere surrounding it. We know that the nuclei of atoms are positively charged, right? They've got protons and neutrons. This means that carbons that are sp hybridized are more electronegative. This sp orbital has more s character. It is more electronegative then. So an sp carbon has more of this dipole going towards it because this carbon is sp hybridized, has more s character, and s orbitals we know surround that positive nucleus. So electrons in hybridized orbitals that have more s character, like an sp orbital, are going to be pulled closely to that nucleus. It is more electronegative. sp hybridized carbons are more electronegative than an sp3 carbon. sp3 carbons have less s character. The electrons reside further away from the atom. As you get to more s character, this atom becomes more electronegative. That means that this negative charge is more stable. On an sp hybridized carbon than it is in an sp3 hybridized orbital. Atoms with hybridized orbitals with more s character are more electronegative because their orbitals are closer to that positive nucleus. This explains why the pKa of acetylene is much lower and more acidic than the pKa of ethane. Let's now talk about the inductive effect. The inductive effect has to deal with what dipoles are present in the molecule. So here I have a series of different carboxylic acids. If I were to draw the conjugate bases of each one of these, and I'm going to show that we lost an H+. So here we're going to lose an H+ from each of these. Let's draw these out. Here's my carboxylate. These are our conjugate bases of these 4 carboxylic acids. The inductive effect shows that if I add electron withdrawing groups. So this is an electron withdrawing group. And it's pulling electron density towards it. We know chlorine likes to have electrons. It is very electronegative. And as we add more chlorines, we actually make this more likely to lose a proton. Let's look at the pKa's here. I'm going to list them up top. So here I've got about a pKa of, I'm going to be a little more specific here, 4.8. Typically we say 5. But now we're going into smaller effects. Inductive effects have smaller effects on pKa differences. So typically we would say carboxylic acid, 5. We're diving into the details around that generic 5. When we add 1 chlorine, we have a pKa of around 2.9. And if we add 2 chlorines on this alpha position, we have a pKa of around 1.3. And if we add 3, our pKa goes down to around 0.7. Now, what's happening here? Well, we know that resonance has a big effect on just the overall acidity of a carboxylic acid. Here's my resonance for this carboxylic acid. But inductive effects are not resonance. It's simply withdrawing electron density through sigma bonds. Okay? So this is through sigma bonds. And you're looking for dipole moments. So as I start to add more chlorines, this is withdrawing more and more electron density, right? Now we know these are conjugate bases, and if we can stabilize this negative charge, they're going to be more likely to form. The reaction is more likely to go forward and lose that proton. So, with more electronegative atoms nearby, this stabilizes the negative charge. Now, we could also compare this to, let's compare this trichloroacetic acid with trifluoroacetic acid. If I have 3 fluorines here, this pKa is around 0.23. So it's even more acidic than trichloroacetic acid. And that's just because fluorine is more electronegative than chlorine. Now, the inductive effect also takes place even if you take an electronegative atom and you start moving it down the chain. So here I have butyric acid, which actually really smells. It smells disgusting. Anyway, don't ever use it if you're in lab. Just try to avoid it. Use a different acid if you can. So here I've got 4 different butyric acid derivatives. And you'll see here that I've got a chlorine on each one of these 3. Now, notice that the chlorine is moving down the chain. It's further and further away from our acidic proton. So let's just fill in the pKa's here. So for butyric acid, the pKa is around 4.9. If I put a chlorine right beside the carbonyl here, the pKa is around 2.9. Now, if I move it down 1 carbon, the pKa jumps back up. It's around 4.1. And then it jumps up even further to 4.5, okay, if I move that chlorine 1 more carbon away. So the inductive effect still is in place, okay? This carboxylic acid derivative with a chlorine on it is still more acidic than our starting unsubstituted butyric acid. But as I add the chlorine closest, you'll see that this is the most acidic of these 4 compounds. And this makes sense because the chlorine we know is electronegative, and that dipole moment is closer to our anion. So this proximity effect is also in place. The differences aren't huge. These are around, what the most is a 2 pKa difference Remember that the element effect has the largest impact on pKa. Okay, so even if I look at two straight up acids, HCl and HF, we know HF has a pKa of around 5 and HCl has a pKa of around -5. So this is a 10 pKa difference. And we've also looked at acetic acid derivatives. If I have 3 chlorines or trichloroacetic acid, this pKa is around 0.7. If I replace the chlorines with fluorines, I don't get a 10 pKa difference. This has a pKa of around 2.3. But the pKa difference here is less than 0.5 difference. So the element effect has the largest impact on pKa, okay? Another thing to note, though, is see how, let's circle the most acidic compound in each of these two series. So in this case, our trifluoroacetic acid is more acidic than the trichloro. And then we know HCl is more acidic than HF. And as we think about this, we're like, wait a second, chlorine, HCl is more acidic. Don't forget that with the element effect, we're also looking at that bond length and the size of that atom. Okay, chlorine is very large. For the inductive effect, you focus on electronegativity only. Okay, the inductive effect is focusing on electronegativity only, and it's how close is it to that anion that is going to form? Can it stabilize that anion? All right. So that's it for this video about why things are acidic. We went over 5 different reasons as to why things are the way they are. You can just look at pKa's and be able to show which side of a reaction is favored. But this video, we dove into why we have the pKa's we do. And by knowing why, that means we can analyze any molecule that we have in front of us. We can describe why it reacts, why something is more acidic. A lot of whys can be answered when we understand the fundamentals of all of this. All right, that's it for this video, and I will see you in the next video.